Hello, thank you for coming so early to this presentation. This is called...
Speak a little louder.
This presentation is called A Proposed Fork in the Road to Relativity. I'm going to talk a little bit about, what I'm trying to do is there's going to be some equation stuff. I want to talk about a little bit of a qualitative type of analysis of somebody named Bernard Riemann and his inaugural address, where he talks about Euclidean planes, which led to constant speed of light relativity, versus something else that I've been developing. A little background on me. I was an electrician in the military, got my undergrad in 2006. I was able to get a fellowship for a doctorate through Wright State University and the Air Force Institute of Technology. I finished my candidacy back in 2011. And at the time, I happened to be working on something called micro electrical mechanical systems. These are like accelerometers that are in phones and everything. And interesting thing is that monocrystalline silicon at the microscopic level isn't.
There you go. There you go. No, no. Yeah, high.
Right
There
there.
you go. Perfect.
Is that it's actually elastic. So glass at the microscopic level is actually very elastic, like a rubber band. And what's interesting is elasticity tensors seem to have a little bit in common with the tensors that we use in general relativity. So while I was doing that, I happened to find out that in general relativity, there's something called the cosmological constant. And then what I found out is that historically, that has been called the constant of integration, which kind of blew my mind because I had no idea how you could have a constant of integration inside of tensors. Basically, there was something wrong with my knowledge. So I started studying a little bit more about it, and I got sidetracked, and as I started understanding more and more about science, I kind of realized that it was possible that everything I'd ever learned in science was probably incorrect. Which, it's kind of like, going to seminary and being a priest, and then coming to find out you find all the books where they put together the scriptures, and people were just picking bits and pieces out of it to put together, and you considered it sacred, and kind of feel a little dumb for accepting things at face value. You assumed everybody else had vetted. So now I consider myself, just to let you know, I'm an unwilling etherist, not by choice, but I learned ether theory from general relativity itself. That's how I came back to it. Last year at the first annual conference, we had Dr. Bartlett here. He's a sociologist. One of the things he talked about was that where does an exact boundary lie between what we can all agree on? Is there a consensus, and is there a point where we don't? So for the past probably 5 years, I would go forward, I would say, oh, okay, I agree with this, and I would go back, and I would go back. My problem is that I have now come to the point where I have to go back 150 years to find something I agree with, which really is a bad position to be in. So I'm trying to think, is there an exact point where I could show where I don't necessarily agree with what's going on? And I think of more of like a soup analogy. That what I've found is that there's all of these ingredients, and everybody's looking at it, they taste something out of it, and the politically correct science says, well, this is what this means. What you see here is what is really physically happening. Everything. We all kind of understand there's different models, everybody has different perspectives and stuff. So what I'm going to tell you is this is the flavors, this is what I see in the equations, and specifically in the geometry. Let's see here. So I'm going to tell you why I don't agree with Bernard Riemann's flavors, what he said was in the soup. Bernard Riemann lived from 1826 to 1866. Just a little brief blurb about him. He's a German mathematician who developed the first rigorous formulation of the integral. That's very important that his inaugural lecture can be directly traced as the foundation of general relativity. So, an expert in integration laid the foundation for our most advanced theory of gravity and the demise eventually of ether theories. So, expert in integration, his understanding, he took something in, and somehow we are where we're at today based on his work. I'm going to jump in so that I can give some context here for what I'm talking about. Otherwise, what's the point of being up here and spouting words if we don't have some type of contextual understanding of what I'm talking about when I say geometry? So this is the very first idea, and hopefully it's so basic that you look at it and perhaps laugh. So this is, what you're looking here is just a line segment. That's all it is. I'm going to call this A, all right? And I'm going to draw another line segment perpendicular to this, orthogonal. I'm going to call this B. And what I'm going to do here is A times B, we can all agree that has area. This is just a conceptual understanding of area. But if I collapse B down, I have A times dB. What I have actually is the slice of area. Now technically in mathematics, specifically general relativity, this is called a one form. But right now there's no functional relationship between A and dB. It's just a slice of area. There's nothing physical about it, it's just geometry, it's an abstract tool. Now let's take another idea instead, and let's start with B instead. I'm going to call this B forward. But I'm also going to draw two others. There's a B up and a B side. So I have three directions. Now that's a physicality argument that there are three directions. But what I'm going to do is I'm going to split these up, the B's. So what I have is I have B side times B up over here, and I just have a B forward. Does that kind of make sense to everybody? A is some constant. And I'm going to say A times B side and B up. Sides and B forward. But on the right side, A is actually another line segment that is no more special than B forward. Both of these have area. The one on your left is a plane. Imagine a plane coming towards you. The one on the right is actually a block of area. So imagine a block of area heading towards you. Plane, block of area. I'm going to shrink both of the B's down on each of these. On the left side, I now have an infinitesimal little bitty block of area. But on the right side, I have an infinitesimal slice of area. They are different. Obviously, I should be able to find some distinction between the two, correct? If I move my little infinitesimal plane of area from left to right, and I keep A constant, then my plane of area has not changed. But on the right side, if I keep A constant also, and I move it left to right, my little slice of area hasn't changed either. So on both sides, I have an infinitesimal block of area and an infinitesimal slice of area. Both of them are moving, and neither of them show any change of infinitesimal area. So if I keep A constant, as I go in the forward direction here, forward, but these are sides, but I'm moving it forward in the direction of the plane. If A doesn't change, then my infinitesimal little bit amount of area has not changed. Over here on the right, same thing. My slice of area doesn't change either. So my little bit of area that I have in the slice doesn't change either. So what I'm looking at here is changes of little bitty infinitesimal amounts of area. The problem is that I look at both of these. If A, if B here, my little ones on the bottom here, if this is a function of the length of A, so it's different than what we normally say. And then over here, I just have A times my little plane of area. What I'm finding out is that the one on the left is going to eventually end up to be something they call curvature. It will eventually end up going to use curvature spacetime. The one on the right, I have a hard time distinguishing from the one on the left, but it says something else. So, hope you guys are probably, I put this in here, you're probably familiar with this equation here. This one up here. This is one of the foundations for special relativity, where you have these little squares here, and now I put minus signs here, but one of these is going to be a different sign than the other. The point is they all equal 0. That, I want you to be able to understand the difference between a square here and the difference between finding the change of area as I go to the right. These two look to have the same form, but they don't mean the same thing, although they still both equal 0. I'll explain a little bit better. So, integral geometry, to me, it's an examination of area, slices of area, and changes in slice of area, and whether functional relationships in them can provide a foundation for a descriptive, quantitative, predictive language of nature. This is not what I started out to do, but this is where I'm ending up at. So what is so important about a slice of area? Geometrically, the arguments with the standard integral, this little thing here, they're actually a particular functional relationship between line segments. So f of x, you might have seen it as y. We're just going to call it a here, is the left side of this slice of area. Why is dx even in here? The reason dx is in here is because you are summing slices of area, infinitesimal slices. This is what dx here is, the bottom part. A is the left, dx is the bottom. So what's so important about it is physically, two of our most important physical understandings of force and energy density are based upon slices of area. The directional derivative of d phi over dx, that which is what is equated to force, that is actually, the phi part here is actually the left side of the slice of area. The dx is the bottom part. You might have heard rise over run, those type of things in calculus. Also, the Poisson equation, which is the geometric expression of energy density. That also is based upon, realistically, slices of area. And as we know, this equation here, as of 2016, this equation describes less than 5% of the energy density in the universe that we know of. So that's why slices of area, to me, are important. But is this functional relationship right here the only one that we can examine? And I would say no. What we have here is two different cases of the slice of area. Well, here's the one you know of. We understand that B here, this x, is absolute. If there's a row of points here, every line segment B is made of the points. But what if I have a slice of area over here where it's relative? So every point has its own line segment B. So over here, the points, any line segment is made of the points. Over here, every point has its own line segment. But they're both still slices of area, two different functional relationships. Over here, my dependent variable is this, and my absolute is said to be an absolute x. Over here is the opposite case. My independent variable is a, this side. My dependent is here. So if I change this, this changes. If I change this changes. They're opposites. So as I go back to look at Bernard Riemann's work, his inaugural address, this is some of the quotes that I'm taking out of here, just to give you an idea of where I'm going with this. One of the most important things he said was something about Euclid. So what happened is he borrowed stuff from Gauss and some other mathematicians. And they were very fond of Euclidean geometry, basically straight lines. That's the way they looked at things. They looked at things as whether lines are not or straight. I'm looking at whether or not what is happening to area. He also said he's not really practiced in the philosophical nature of stuff, just more in, where the difficulty lies in the notions themselves. He's basically saying he's a good mathematician, but when it comes to philosophy, he didn't really have an idea of it. And then he started saying, well, he believes in something called quanta, which is quantity. And quantity is measuring. But measuring means you can only measure one thing relative to another thing, something else. So there's nothing absolute in what he was looking at when it came to geometry. He was just using relative things. So two magnitudes can only be compared when one is more or less than the other, not how much. So to me, this is what we're looking at here, is the foundations of relativity with geometry. So he also sits there and says, well, it's only possible, a continuous progress from a point is possible on two sides, forward or backwards. To me, he's talking about differentiation. He's talking about comparing line segments. And again, he says here, every line is measurable by means of every other. So everything is relative. He says it's relative looking at just line segments, and the way I'm viewing it, starting to view it, is that it's actually relative area. So let's see here. What he has down here is that ds squared is multiplied by a constant, and dx is equal to ds. So somehow I'm getting ds squared multiplied by a constant, which, as I showed you before, is the two sides of two line segments of a plane. He's taking just some constant. He says, well, I'm just going to multiply this constant by these things, and then I'll see what happens when my constant changes to the plane. And then he has some more equations down here, and as you notice, there's a little theme in here. This, to me, looks like it ends up being a slice of area. These are slices of area. I have my side and my infinitesimal little bitty width at the bottom. He also says that right here, from flatness, which is what he describes as being a certain property of them, is the surface direction. I underline surface direction to understand that when you look at a square of the dx, they're talking about, he is specifically talking about a plane, and that there's a direction of the surface. And he says also that the whole of planimetry, everything about a plane, must retain a validity. But on the other count, it's different from a sphere, which cannot be changed to a plane without stretching. So to me, the stretching part is the same thing as the x as it being relative or absolute on one hand, but we're still looking only at geometry. So these are the questions I end up having about when I was doing this, as I look into mainstream physics. Why is the cosmological constant, it's called a scalar multiple of a metric, described as a constant of integration? Geometrically, isn't a constant of integration graphically just a line segment? When we measure rates of change of area, the area under a curve and under a function, the constant of integration is basically the line segment on the left. We are only measuring, when we take a derivative, we're only measuring how much the area changes. We're not actually measuring how much area there is. That's not what a derivative gives us. It gives us how does the area change. Why is there not a unique definition of flatness in general relativity? Any metrics that fulfills this little bitty thing here is called flat. So they have an infinite number of definitions of flatness, but they only choose one to describe the universe for that matter. If a plane is made of just units of area and the plane changes, aren't the units of area changing? Can we just look at the units of area instead of the plane? If we're taught to examine a plane to see the lines are straight, and we change that plane to imply the lines are no longer straight but are curved instead, if changing the plane changes the area, shouldn't we instead of curvature, we should be understanding and looking at changes of area? If we're summing slices of area under a curve to give us total area, and when the concept of differentiation gives us the change of the slices, and differentiation gives us differential equations to describe nature, could we use just slices of area to describe nature? There's in general relativity and also special relativity that we have in it's called the Minkowski metric. They choose the number 1 to describe flatness. And if you can choose any constant number, that's what the cosmological constant means. You can choose any constant number to describe flatness. Why do we choose the number 1? Why does the Schwarzschild radius solution have the structure of two planes within a point to cancel out? This 1 minus 2 phi here, you can go to a NASA website for kids, and what they'll do is that you can calculate the radius of a black hole. What you're ended up doing is you're solving for 0.5 here. So you're solving what would the radius be to make this 0.5. From general relativity, this one here is actually 1 dx dx. And this is 2 phi dx dx. Now, as you know, that dx up here is cdt, and this is cdt. So what they're doing is they're holding this constant. They're saying, well, my limiting function is a 1 way out, and this one's a 0. But if we hold this 1 as we come in, at some point, this is going to be a 1 also, whenever this is 0.5. And I get 1 minus 1 equals 0. Why? Why does that? What's important about that? I mean, geometrically to me, it looks like we're doing nothing but canceling out slices of area. And that's the whole, is that the point of it, is that general relativity, the flavor, the quality of some of the solutions appear to be actually be slices of area and not planes. I mean, I can understand why the analogies are there, but the formulation of it is leaving something to be desired for me. Some more questions. Why are space and time able to be represented by line segments, but not energy and momentum? So in special relativity, you're always using line segments to determine length and path and everything. But why don't we do that with energy and momentum if energy and momentum change space and time? That doesn't seem, it seems a bit of a flaw in the logic. In the mid-1950s, there was a scientist named Nathan Rosen, and he came up with something called biometric gravity. And his biometric gravity, he said I have two metrics. One's constant and one's dynamic. To me, it looks just like a line segment where you're holding one end constant and you let the other one vary. It has the same properties, it's just another line segment. But why does general relativity borrow the Greek letter rho and the letter p from a perfect fluid for energy, density, and momentum, if ether theories have no validity whatsoever? Why did Schwarzschild analyze the interior of a spherical body made of a perfect fluid with density and pressure instead of energy and momentum? What does his analysis mean if all matter is over 98% nothing? What was he really actually analyzing? Why does a report sanctioned and functioned by the DOE, NASA, and the NSF consider dark energy as possibly a vacuum energy density and a perfect fluid that is everywhere? So there's a bit of a cognitive dissonance on what I read in the textbooks and what everybody else happens to be saying to each other. So we're throwing these perfect fluids around and describing them, but we're also describing them as energy and momentum. There seems to be something being lost in, we're using the same words to mean different things. And could the ether best described as a point function? By a point function, I simply mean what I showed earlier, where B is a function of A. Right here. All I'm looking at is whether or not this little slice of area here, now that's a point, is a function of the length of this. This equation up here, this ds squared, from what Riemann wrote, this here is the sides of my little plane. And then I have my little constant out here, which he described in his inaugural paper, which ended up being called this metric G. Well, how do I know that this metric G actually isn't A over here, another line segment? These are to the sides, this one's forward. Go back up. If there's a constant multiplied by this G, and there's no explanation for why it's there, are we just looking at the other side of this slice of area? We're not actually looking at whether or not the plane changes the area, we're actually looking at whether the slice of area changes as we go. So are lambda G and G just specific interpretations of A? So basically, to me, general relativity is actually a very specific relativity. It's a specific interpretation of geometry. So is A, so my question boils down to this. I have an A here that I have called a point function. Is A just a number or the side of a slice of area? How do I tell A from G? How do I tell the side of my slice of area here as I go forward with the relative point function? How do I tell that from the G here? So far, that's what my question boils down to. Is that forget all about the what we're saying physically or anything else, but geometrically, how do I tell the difference between the two? Because the qualitative properties of manifolds and surfaces and everything, for some reason, don't explain the singularity, nor do they explain the constant integration. Should this number ever be a 1? Why would the length of this ever be a constant 1 everywhere? If it was my choice, I would just choose 0. If I'm going to make a model of the universe with no matter energy, I certainly wouldn't choose this to be a 1. According to this is going to be a 5. It's going to be a 2,036,012, as long as it's constant. That's all it says, is that the relative area isn't changing. So this little point function, I call this a gensor, and it's nothing but geometry. I'm just looking at 2 sides of a slice of area. The reason I have gone back to being an etherist is that if my side of my slice of area can be interpreted as the metric G, and the cosmological constant is actually the vacuum energy potential density, modeled after a perfect fluid, then that means that the change in the density of the vacuum is, I would say, this is physical and this is geometrical, the length of the line segment. If there is no change in the density of the vacuum, then this line length is 0. To me, that's just an isotropic homogeneous fluid. So that means there's a fluid with no changes of density in it. And which means also that what we consider energy density is a specific equation of where we're looking at the ratio of the change of the vacuum energy density over the change of space and time, which fits with what ends up fitting with what Einstein thought at first. So see this little r equals 0 here? I can't tell the difference between what he's writing here and what's on this metal and this equation here, which ends up being conservation of energy and momentum. That's what he's trying to write here. The problem is this is shorthand notation to describe a complex idea. I don't know a way to tell the difference between this and this. And I just ended my presentation. Any questions? So my question is this: did any of this make any sense whatsoever?
Yeah. Well, I have a whole different. My bachelor's in advanced calculus.
Right.
And I love calculus and mathematics. I found a world that was perfect.
Mm-hmm.
I mean, when we started working just all this time, I came to a very weird conclusion. I write this in the book. In fact, I put it in the book, and I wasn't sure it was good to put in the book. And I literally talked for the first 80 pages. I said, there's no math. There's math to explain to the average person what calculus is. My father, when he was doing, I think I'll come over here. My father, when he was making
I get the blame, right?
model for gravity, was summing up little forces. Because there was something wrong, in my opinion, about calculus, which I loved, and having that as a model for the universe anyway, because of the infinitesimal part of it.
Right.
I couldn't make physicality out of that.
Right.
And so what you had was Newton coming along and supposedly laying the foundations for calculus, which of course was refined over the years. I think some of the people think that he invented integration and differentiation, and all the little symbols were there. They're not. It took a while to develop.
Right.
And it is quite amazing to me that when you can use mathematics and find an area under a curve that you just, in your mind, it doesn't make sense. You can't look in the physical world and understand that.
Right.
But you can understand it intellectually with integrals.
Right. And where you can use it as a tool to help see if that explains the way things, explains nature.
Yeah, but that's where I'm going to say, this is where I don't think that's true. I think what's true is that we can use it in engineering to get answers to things where we need to, because we're trying to find something about it. But I think where we go wrong is we try to use a model. And let me continue the story here. My dad, when he was calculating gravity, wasn't in the integral world. He wasn't in calculus. He was summing up F equals ma in little forces as a cloud. It took me, I don't remember, was it 2013, I came over to his house and I said, look, you're doing a different mathematics now in the sense of modeling. Newton didn't have a machine with 6 processors and be able to go to 150 decimal points like my father does and run it for what's the longest program you ran?
4 days.
4 days. He couldn't add those up, even though in his world in the beginning he was talking about little forces. I mean, let's face it, computers were human beings in the 1800s because they had to sit down and calculate charts for people who were mechanics. They didn't have computers to use this. And in my book I talk about this, that computers simulate all these things that are perfect in mathematics in absolutely imperfect ways, in digital form.
Right.
So what I'm saying to you is I think one of the problems is we try to use calculus in a world that can't, in my opinion, you're talking about it's an ether. It's not an infinitely dense impossible, because my father said something very profound at this time. It's a continuum can't apply a force.
Right. Well, see, the way I look at it is that I'm not really caring whether or not this even models reality. What I want to know is, how did you arrive at some of these equations? All I want to look at is the geometry. And then step back and say, what about this geometrically are you assuming is equivalent to nature? Where are you getting this concept of the conservation of energy and momentum and everything? So that's what I want to understand, the geometry behind it. To me, special relativity, if the side of this is this is my independent variable and this is my dependent. Special relativity, to me, is just the squares of the dependent variable. All they're doing is varying little blocks of area to conserve it, and that's how we end up with, special relativity has nothing about energy and momentum in it, correct? It's all about speed of light, length, and time. And all they're doing is looking at the dependent variables, and they're varying those as line segments, and they're conserving the area. To me, it's just a geometric riddle, it's a trick. Yes.
So, I find it very interesting as far as I understand it, that attempt to reconstruct, to get from the formal theory, right, back to the elements of the physicalities, like ether, densities, and so on and so on. But one more thing I believe very important, maybe related to this one. So, in my presentation, I kind of attacked the practices, starting from Newton, to look at the fields as potential fields, as we had here. On the other hand, to rely on the energy conservation and momentum conservation, angular momentum conservation, as constants, no time varying and so on.
Right.
And have indicated how it has one has come to it, how the genesis of it, and the fact that very method of concurrent using of energy conservation and angular momentum conservation has gotten mass again back into the equations, although in the differential equations mass figures on both sides and can be cancelled out. So my suggestion would be, or question, if you would be taking those elements, those aspects into account, that in my view are very basic fundamental errors and misconceptions or flaws in the foundations of Newtonian mechanics that has been, of course, proceeded to
propagate
general
that through.
relativity. Would that then bring some kind of life into the structures and then really get back to the ether and then somehow get
Okay, right.
consistent?
So my idea, my focus is to try to. All I want to know is that what are we saying in the most basic language, and what is everybody else assuming about that geometry that is related to mass, or why do we? What about the geometry implies energy and momentum conservation? Why do we even bother using this? So, where did it all start? I do think it started with Newton. I think it started with Newton. Whenever his original construction of understanding of the infinitesimal, and that to me that is where the problem started. Because this part here, this is going to end up being dx. But the problem is that in a field potential, this dx is considered absolute. I move a little bit infinitesimal. You're saying that I'm moving an infinitesimal amount. This is where the field potential comes from. This is where a derivative comes from. We had that in our head, and we just assumed that once I took this, and I'm multiplying it by my little bitty slices here, and this is a plane, to me that is actually comes from Newton, because now we're changing the plane. And so, hey, I have a plane, I have area, and so this seems to fit with special relativity, with the concept of c squared d squared on the sides here. I think the reason that this actually works is because you're not examining actually the little blocks of area here. It's actually because you're actually examining whether or not the slice of area changes. I'm not saying this is physically correct. I'm not saying special relativity is correct. I'm just saying that what they're saying, writing here, is actually a misunderstanding of this. If you understand this, then you can understand why there's a cosmological constant. Not physically, but why there's one geometrically. If you understand that, then you can understand also why the Schwarzschild radius exists. Why do we solve for that? So I'm hoping to write it all in a more basic language to compare to what is already here, and then just sit there and say, well, this is what we're doing here, whether or not it's physically correct.
One more point. So you are addressing relevant aspects at the level of mainstream physics.
Yes.
Yeah.
So I believe it's very important if you would be considering, taking into account possible, as I have indicated, very basic problems regarding the reliance on the potential fields only, and then have energy conservation to get something, have it something as in charge, or to have the role to take care about the radial direction, and the angular momentum to take care about the angular directions. So yeah, those basic kind of problem with potentials as conservative fields,
Right.
and then reconstructing non-conservative fields by going with these two laws. If you would
Well, see,
take those things into consideration, then maybe more acceptable somehow. People would be more receptive to see those potential effects.
but I am 150
On that
years
level,
behind, one person.
You mean you or we?
Well, right, but we're all interested. We'd all love everybody else to do our own, to help us out on our research, but.
Yeah, but maybe familiar with methodology,
Right.
I could do it on the level of the Newtonian mechanics very easily. And I believe it would be easy for you with people if you.
Well, I'm hoping, here's my next goal, is I'm hoping to explain this in the most basic way I can about relativity. So I do have a possible physical experiment, it's a qualitative experiment, which would end up lending credence to the way I'm looking at this. That would distinguish, what I mean by qualitative is, I give you a kind of analogy, is that, so I'm an engineer. Imagine that I was able to build a device where I said, well, if I pass current through this, I can make the resistance go so low that when I do electricity through it, it moves pretty fast. But if I build this out, I can't send a signal at a high rate of speed. But what if I could send a signal that was faster than the speed of light? Simply based off of this. I couldn't tell you how much faster, but would it matter? As long as it was faster. Now, I can't do that. I'm not claiming I can't.
You can. I can help you.
But I do have another experiment. It was actually an idea by James Maxwell. And I think I have another way of building something that he proposed. But it's not going to be, it's only going to be qualitative. So my focus now is to refine this, and then there are investors out there who would help try to do a proof of concept. But I don't know that yet that I'm explaining this well enough to even people here that have an understanding of relativity, or even ether theories and stuff. So my question is, I got to figure out by myself, how do I explain this to a layperson enough to where they want to fund a proof of concept?
If you would like to do that, of course, one thing is that might be useful, not to really clash with the established dogmas, right?
Right.
But to implement it, you cannot rely on the special relativity postulate. Right? To implement it, you have to think, believe, or somehow assume that the classical Doppler shift, like Galilean or whatever, B over C, is reality. And then there was that kind of micro-mechanical stuff in your biography. I said to my friend, okay, I'm going to talk about this guy. Because I had also proposal, and for macro experiment measurement, there was one slide here, and proposed technology, like fully optical routers, multiplexers, and synchronizers. And was interested in your micro-mechanical devices that had to consider structures that would rotate enough speed, with enough speed.
On a microscopic level?
Yeah, to induce enough advancement and delay of the signal. You remember those three triangles that I was drawing? So let's talk about it.
Well, we could the problem with MEMS is that they had a lot of promise back in the 90s, but what we found out is that at the microscopic level, surface charge and all of these other forces are massive. And so things don't really work quite as well. So simple devices like accelerometers work really well, but to actually try to do little gears or any type of little moving device, nobody's had much success with it. That, you know, which it just, yeah, we'll talk about that later.
I was just wondering if you're familiar with something called smooth infinitesimal analysis. It's a different version of calculus, which it views all functions as being continuous and incapable of being expressed in terms of
Is that like,
discrete.
that might be like finite element analysis.
It would disallow finite element because it views all functions as being continuous and incapable of being expressed in terms of discrete entities.
Well, I think that's almost kind of what they call a manifold about.
Okay.
This is where he says manifoldness, whether something's differentiable or not, whether it's connected. I'd have to look into it.
Yeah, I mean, what defines it is that it does not accept the law of excluded middle as a proof. So it says that it doesn't say that if one, like for the square up there, it doesn't allow. It says, you can't do proof by contradiction, so you can't assume that, proof by contradiction, assume that one statement's false, and then that implies the opposite's true. It doesn't allow that, and so, the result is that.
So if you can't prove there's not a God, that means there is a God. You can't prove it by contradiction. Is that what you mean?
Right. Yeah. But that's based on intuitionism, and it's the idea of it's a constructivist theory.
Okay, I'd have to look more into it.
Yeah. We're looking at the mathematics here to evaluate the theory of relativity, and in the work that I did in electrodynamics, I showed that by using the complete set of the empirical laws of electrodynamics, you obtain the same results in electrodynamics that you get by combining electrodynamics of Maxwell with special relativity, but you don't get it from any of this mathematics. You get it just from the empirical laws. And so what you have is two different approaches, and now you've got a problem. If electrodynamics is true, and special relativity is true, and I try to combine electrodynamics with special relativity, I get double the effect, which doesn't agree with theta. And so you have logical problems here, and the problem is which is true. You got the same formulas coming from multiple theories, but they can't be applied simultaneously. So if relativity theory is true, and you apply that to electrodynamics, now you get the wrong answer. But when you do electrodynamics better. And so the problem is that in math you can, in theory, have a million ways of obtaining the same equations. So how do we distinguish between one approach versus another approach?
Right. Is there a distinguishing characteristic of these that doesn't show up in the others, but the one that does predict it, it actually shows up in nature?
Yeah.
I mean, what's the most appropriate language we have to describe nature?
Right. So anyway, I'm saying that special relativity is in opposition to electrodynamics. It's not compatible. And so that's a problem. And we don't need special relativity anymore, because from electrodynamics alone, we get the results that special relativity has predicted, and we don't have any special relativity, we just have electrodynamics.
Right, so what would interest me, though, is that from the point of view that I take it, is that how did Maxwell develop his equations? And geometrically, what do they mean? And what's the difference between the basic geometry of, Maxwell's curl and all of these other things, and the geometry that special relativity is? I'm looking for the exact point where we start from something, they're both the same. Where do we change from? And to me, there's something in general relativity in these vectors called covariance and contravariance. And what I suspect is that there's a function called a contravariant point function, and that I can end up, I'm hoping, I'm gonna see whether or not I can reconstruct Maxwell's curl out of it. So maybe there's another way to look at Maxwell's equations simply with a different geometry. And so and I would be able to take that and compare that to special relativity, and I would say, this is the link we have here. And this is the this is where these characteristics come up geometrically as you look at them differently. I'm not sure if that answered.
I was also another comment you made about boundary conditions and things of that sort. In electrodynamics, if you use the complete set of the 6 empirical laws of electrodynamics, and you derive the acceleration and the dAdt, or radiation reaction term, you have a first point where a boundary condition enters. You get, when you're deriving the radiation reaction term, you get 3 terms. 2 are subject to boundary conditions and 1 is not. The one that's not is the one that we believe describes what we see experimentally. And the other 2, since they don't appear experimentally, we think they must go to 0, but that's a boundary condition, and that specifies how all matter and charges and things are built. And so the boundary condition is very important in that sense. And so if we, and I think you're seeing that same kind of idea here in your analysis, that boundary conditions play a role.
That was the thing I was talking about with the smooth. It specifically, smooth infinitesimal analysis specifically says that just because the dA goes to 0 does not imply that any of the specific things go to 0. You can have infinitesimal equals 0. You can have an infinitesimal without implying either of the sides go to 0.
Okay, one more question. Go ahead.
Yes.
You have 2 more.
We have classical mechanics, relativistic mechanics, and quantum mechanics. We have special relativity. We have general relativity. Does it mean that we haven't got the hang of it? Or there should be one system of mechanics or electrodynamics applicable to all bodies at all speeds. Nature is consistent.
I mean, my opinion, well, actually I don't know. So what I want to know then is, if that is true, does that mean I can take this concept here and reformulate this to cover everything?
Yes.
I don't.
In the way that I may just suggest how
Right.
it works.
So could I take this?
Somehow to reformulate it, to be able to really reflect the dynamics of the nature,
Right.
Eight dynamics.
How
You can
many
go
more?
from the
David?
beginning, right? Like many people have
David?
done that.
David,
I can provide some information.
how many more speech
But,
speech
here
gave
we
away this
really
morning?
somehow to-
Not too many, I don't
to
think.
Can I say one more thing?
We'll see.
change
We'll
the
see.
type of the field somehow avoid the separate utilization of energy conservation, so just go for the minimization of work and things like that. But okay, the other way would be easier. Okay, that's out of scratch, right?
But I do have to admit, I am
Yeah.
partial to his bias. I do agree that probably nature is simple, and we just don't have the correct language to describe it, and everybody's dancing around the correct language. I don't know that this is it, but I do think that we should, if as natural philosophers, we should be examining how we are describing nature. And to me, I'm just examining exactly what are you saying geometrically. What did Riemann mean when he took the sides and multiplied them by a constant? To me, I want to drill down to what does this individual term mean here? Eventually, this is going to end up being dx, which is going to be c dt, and they assume that c is the velocity of an electromagnetic wave. The way I look at an integral and everything, I don't think that's going to end up being logical. I mean, I'm not a fan of special relativity simply because to me, I think what's going to end up happening is that you will end up, if you're on a spaceship and you start going toward the speed of light, or even in gravitational well, I'm okay with time dilation. But I think that the construction of the clock is going to end up coming into play because I can have two clocks that are ticking at the exact same rate, but as I take them down an electric well, and if they're exact same construction to the identical, then I have no problem with them ticking at the same rate. I have no problem with them will end up ticking differently than one at a different potential. But I think if I take two different clocks, and one of them's Big Ben, and the one of them's a cesium atom, I think what will end up happening is that as you go in a well, they will both start ticking at a different rate. I'm okay with time dilation, but I think that it's based on the construction of the clock, which is going to end up being based on probabilities of how the waves interact.
I wouldn't call it time dilation. What you're talking about, we call, at least in this group for many years, is clock retardation.
Or yeah, to me, as far as I understand it, to me, I view it as a physical change of the rate of events. So, I'm assuming.
Yeah, to say time is moving, that's what I'm saying. That's why. That's just a thing. One more question here.
One more question.
Yeah, I believe that ever since the debut of relativity, the physics study go in the other direction. The direction is people more and more using mathematical conclusion in place of physical development.
Yeah.
One of the typical signs saying this is that the so-called wall line in the Minkowski space is typically using human perception in place of nature. In Minkowski concluded with the general relativity, we have this famous conclusion saying that the words UN from event 1 to event 2 is going on a straight line in the Minkowski space.
Mm-hmm.
Okay, to me, it is absolutely not that way. For example, if I want to have an event 1 on the north side of Great Canyon, I want to have an event 2 being at the south side of the Great Canyon. The shortest, fastest way I can do is jump, run, and then jump across that Grand Canyon. But the wall line, actually, if it exists, you bring me to the bottom of the Great Canyon, never to the other side.
Right.
Possibly, a bird has a better wall line because he can fly to the other side. And then Donald Trump has an even better wall line because he can buy a helicopter and fly to the other side. So I can't accept the wall line concept. It's a completely human concept. Yeah.
And it's a good point because, like you said, Bart, he talks about events where this B here, let me go back.
Mm-hmm.
So the way they describe B here is I have at one point an event and I have another point another event. And so I have a delta, we'll call it B and another B. They would call it delta B. And they're calling this an event from one to the other. And so when they shove this down to be dB, that's where he views it as. Me, I'm just viewing it purely geometric. It's just a line segment that I have collapsed down to zero. I'm just looking at an area. He has given a physical, or more of a philosophical model to what the geometry says, where he's using events between two things, where he gets proper, that's where they end up with proper distance and proper time.
Another example is the Mercury procession.
Mm-hmm.
After the Einstein using the general relativity and explain the Mercury procession, everybody said, oh, general relativity is great. However, in his calculation, he completely ignored the history of the development of this orbit. Okay, commonly accepted the solar system exceeded at least 4.5 billion years. During the 4.5 billion years, a lot of physical events may have happened affecting the precession, the orbit of the Mercury. And even nowadays, if somebody can throw a stone at the Mercury and the stone will stay there, I guarantee that next 2 centuries, you will see a different orbit of Mercury. The precession is different.
Just one comment. So when you mentioned the precession of Mercury, Einstein's solution for that,
Yeah.
it's very interesting that the very same formula was in existence for 20 years before. There was one physicist in Austria who published paper, say, 20 years ago. So Einstein, as he always, he was just fitting, because you don't have basic principles. You just was
That's
looking
not
for
a
something.
basic principle in that.
The formula from us.
Backward engineering.
He wanted actually to get the kinetic energy when V goes down to zero, right? And then he had to reformulate and to get this. But again was there before. Things are there. So I mean, but regarding the precession would be actually something, in my view, either as a neglection of the non-constancy of angular momentum, or essentially spiraling movement, as Dr. Ruklas just mentioned, that he was in chance and was requested to kind of correct, smooth out trajectories, right?
Can I continue, please?
Yeah.
Okay.
Well, what's crazy is Einstein uses this precession of the rate of perihelion of Mercury as a confirmation of his theory, and the big effect, which is the quantization of the orbits, which is much, much bigger. Big dogs altogether.
Or the other thing is that we have the precession of the perihelion, or I believe that's how it's pronounced, and that's supposedly a confirmation of general relativity. Yet when we go out to galaxies, it's nowhere close. I mean, I don't have any idea about dark matter and why the angular, why they're spinning so fast. But it's funny that on one hand the perihelion confirms general relativity, but yet the rotation rates of galaxies being so fast does not disprove it. So, I mean, to me, it seems kind of like selective observations.
Yeah, and during the 4.5 billion years, a lot of comets, they have hit the Mercury and changed its orbit and left the current orbit for us to observe. And also, because of the short distance between Mercury and the sun may also have, with the high temperature, may have evaporated some mass out of Mercury. So during the 4.5 billion years, the mass quantity of Mercury may have changed, sometimes up and down, and definitely it will affect the orbit of Mercury.
I mean, just talking about changing of mass, I mean, what's interesting is that what most people don't know is if you look through the history of general relativity, there was a conference where they had two theories. One of them was general relativity, and the other one was Gunnar Nordstrom's second theory. And Einstein worked on that one also. So on one hand, you had curvature of space-time, and it's curving space-time more. In Gunnar Nordstrom's, mass was variable. So they were looking at two separate ideas, But why does nobody talk about Gunnar Nordstrom? Because was it disproven? No, because everybody liked general relativity so much better, so everybody died off that was following Nordstrom.
Okay, speaking about curvature.
Okay, we're going to have to wrap it up last. Okay, thank you very much.
Okay.